Hello everyone, this is Bradley. Today this is a voiced recording to make an animation people asked in the Discord server. I decided to make this animation because I think this is a very good opportunity to talk about some very basic, boring ideas of simulation. And it may be a kind of reference whether you're interested in or not. So let's start. So here we're in Blender. As always, I'm going to use the presets which you can download for free from the link in the description. Let's go to the node editor. Firstly, let's discuss the principle of this setup. Basically, what we're trying to do, as shown in the reference from Cinema 4D, is that we're going to emit particles. And when particles reach a certain area, then we are going to turn the velocity of particles to the other direction. So here, let's firstly create a node tree. I'm going to use a procedural grid to emit particles. And let's take a point distribute so that I can set the amounts clearly, instead of using the distribute points on face where we are setting a density. And then let's try to transform the geometry, maybe to the y-axis, so that I can emit particles to left or right. Next, let's use a simulation zone to move these particles. And within this simulation zone, we are going to just set a position and offset it. And the simulation zone is basically running a loop every frame. So if you set the offset to 1 meter, then you can see this particle is moved to the right. But then next frame, the result will be feedback to the simulation inputs, and you run this set position again. That's why you can see this point gets moved a little bit more. And if you start to play this animation, then this particle is moving. So here, let's just increase the length of my timeline so that I can keep watching this movement. Right now, the velocity of my particles are quite fast. So I'm just going to give it a small enough value. And you can use delta time. It's basically just counting the time, the real time in your Blender. So for example, maybe my animation takes 3 seconds, and regardless of the frame rate, this delta time will be quite stable. Because even if it's 3 seconds, for 60 frames and 24 frames, 1 meter per frame will mean a completely different result. So sometimes you may want to delta time to get a more stable velocity or values inside the simulation zone. But if you do not understand the concept of it, you can just think that as a small enough value. As you can see, this particle is moving much slower than previously. And for a consistent frame rate, it's basically the same as you just take a value precision. In this case, this is 3 divided by 100, so this is 0.03. And you basically get the same result in this case. Okay. So right now, we already have this particles movement. And just to better visualize the path of its traveling, we're going to add a tracer, which is generating a trails of these particles. And you can trim that. We will discuss this later, but right now this is fine. And then we are trying to rotate the path of it. So we can take the rotate vector to rotate this velocity. However, you can see that this is just a one-time rotation, because we only rotate it 1 time and the velocity is not being updated. So in order to update the velocity, on this rotation, we need to capture a velocity attribute. There are two ways to loop the attribute, just like we're looping this geometry. You can either feed these attributes inside the simulation zone. Then you can see there is a in and out, just like the geometry sockets. Or what you can do is to store a named attribute. Here I'm just going to store named attribute instead. So let's store a velocity attribute. So we start with this velocity, and I'm going to use this named attribute inside the simulation zone. And this velocity is a vector. And once I'm rotating this vector, I need to rewrite this velocity to a new one, and I use this velocity into the offset. Here, this might sound a little bit confusing about what I'm doing, but this is a very basic concept of fields that even if these two linkages come from the same node, but the value is actually always stored in the geometry. And with this new store named attribute, this value here is being rewritten. So these two are not the same. These two values are not the same. Okay. If you aren't sure about what you are doing, then you can definitely duplicate that. The result will be 100% the same. But anyway, so now if I play this animation, you can see this particle is keep turning itself, and finally it forms a circle. And by manipulating this value, then you can see a different speed of turning. Right now, there are two problems that we need to solve. One problem is that this particle starts to turn at the most beginning, but I want these particles to turn only after getting into a certain area. The second problem is that you can see this particle is turning endlessly, but I want it to stop after turning 90 degrees. So we're going to solve the first problem with a fold. So we take a proximity fold. I talked about this node in many different cases. There is even a separate tutorial talking about it. But the basic idea is that we can better visualize it with a spherical empty. And at the center of this empty, we get a value of 1. And as it goes outside, you get a value of 0. Okay. And I'm going to better visualize our path with a bevel curve, so that now if I emit the particles, you get the kind of volumes. So let's decrease the radius a little bit. Okay. And yes, we basically just put this fold into the combined Euler rotation. And let's move that closer. So if I go to the X view, and you can see it was kind of shooting straight at the most beginning, but then as it get close to the center, then you have a larger turn in this fold. And I want them to turn at the same rate once they're getting into this range. So I'm going to use a greater than, and then you can see that they start to turn at basically the same magnitude within this fold. And since this proximity fold is in the range of 0 to 1, we can remap 0 to 1. And this is basically just a map range node, but you can see it's much smaller and cleaner to manipulate. So if you want to turn a higher magnitude, then you can just increase this number, then you get this result. But we need to solve the second problem, that is to clamp this rotation to 90 degrees as an end result. This is a very tricky question. But it's also a very common thing when you're working with simulation. That it's very easy to start with an animation with just a single value, but it's very difficult to know how to stop it or how to define the destination. So here we're going to play a trick of working with mixed node. I'm going to create a two state of velocity. So one state is that I'm using this original velocity, and the second state is I'm going to define a destination of rotating 90 degrees. So if we keep this factor as 0, then we are fully using this initial velocity. And if I play this animation, you can see that my particles is only moving to the right. But as I'm increasing this factor, then you can see it starts to turn gradually and finally approach the state of 90 degrees, which is the destination we're looking for. And the next, what we need to do is basically just to manipulate this factor relative to our proximity fourth. So if I directly plug this proximity fourth result into this factor, you can see that because I have this greater than, then immediately it starts to turn 90 degrees to the destination. But because it goes outside this fourth area, then the factor very soon becomes 0 again and finally recovers its full initial velocity. So we need a way to memorize this state of turning. To do that, basically we're going to do the same as what we have done previously of writing velocity, but this time we are writing a float value, and I'm going to name that as an F, which stands for fourth. And if you directly plug this greater than into the value, and let's reuse this newly written attribute into the factor, you are going to have the same result as previously because you are keep rewriting this F value every frame based on the current state of this proximity fourth. So in order to make it memorize itself, we're going to add the previous fourth value onto itself. So the previous value will never be deleted while it's always being newly used and updated based on the new conditions. So now if we play this animation, you can see it just turn 90 degrees one time and it will keep memorizing its state. Right now you will find that this turning is a little bit too sharp because it happens immediately as you get into this fourth range. That's why you can use a remap 0 to 1. And let's decrease its value a little bit, maybe 0.2. So now if we play this animation, you can see it turns a little bit slower, like taking 5 frames, but it's not a small enough value. So let's take another value position. This is 0.01. So let's plug that into the value, maybe 0.05. So now if we play this animation again, then you can see this turning becomes much more smoother. And you can try to play around with these kind of values to make it smaller or more smoother and so on and so forth. But just to know that if the value is not high enough, sometimes you will get outside the zone before you finish 90 degree. So this is kind of a parameter issues and so on. But what you can also do is to try to place these fourth a little bit differently, so that you just want to make sure that these particles will stay in this fourth area long enough so that they can finish their turning of 90 degrees. Okay. And of course, you can increase the speed of these particles movement and so on. So these are things that you can play around when you're working with it. So now we have finished the major concept, and the rest we're just going to finish this setup with some changes. So one thing I'm going to do is that instead of emitting a particle once, I'm going to emit multiple particles, and I'm going to have multiple traces. So one thing I'm going to do is that I'm going to train these particles. This tracer by itself is running a simulation zone inside. That's why you want to keep this train value as small as possible, because otherwise it will train at a very fast rate and you only left a kind of a short tiny segment. So try to keep this value small, or as you wish. Does not really matter to me, but anyway. So now we have one set of particles and one set of tracers. We need to emit multiple particles for multiple tracers. The way we are going to do that is basically to join geometry. And by inputting these particles inside the simulation zone, as we are running this loop over and over again, then you will keep adding these particles every frame. So now if I play this animation, you can see we do not have the training effect. This is because that the particles are spawned at the same locations every frame. Here, I'm going to change the seed with a same time frame, so that every frame you have a different seed, and you can see every frame you are having different particles being emitted. Okay. If you want to slow down this emission, what you can do is you take a switch. And obviously, if you do not turn on this switch, then you are not emitting anything, and you turn on the switch, then you emit stuff. So we're basically going to change this switch with a module for. It's running a time inside. And basically it's a kind of modulo function that every time this modulo gets into 0, you output a true, and so on and so forth. So by playing these values, maybe 15 frames we get a true. Then you can see every 15 frame we are emitting particle once. So this is just kind of an idea. And if you want to emit these particles at the first frame, you basically just offset by -1. This is a basically kind of math trick of this modulo function. Okay. And next, I'm going to give a different color for these particles and the tracers. To do that is a little bit tricky, but I already prepared this set particle parameter. And as you may see that I also defined a velocity in addition to the ID. So here I'm just going to replace these velocity definitions in this new node. And you can see there are some parameters of directional variances or other things. It's not very important here, so I'm going to just remove these directional variances. So it's straight, but I can keep these velocity variances. Okay. And I'm going to rewrite this ID with a new store named attribute. I'm going to discuss why, as we are going to set this material. So for our plane, I'm going to create a material emission shader, and let's go to the shader editor. If I'm going to write this ID, so let's take an attribute, and we named our attribute as an I. And if I use a white noise node for a different color, and let's visualize that in the material preview. This looks kind of okay now, But if you change your views or perspective, then you immediately find this weird shading artifact. This is very bad. And yeah, it also occurs in cycle. And this is a known bug. Actually, this bug is known for 3 years, and I don't expect it to be fixed anytime soon. So the solution here is that you have to take this named attribute I, and you need this white noise being set in geometry nodes. So you can either use this value or you can use this color, whichever way you want. But I'm just going to name that as a W. So instead of using the white noise texture, I'm just going to use this W, then you fix these bugs. If you want to specify colors instead of using random color, then definitely you can just use the value size of this white noise and you can set this color. Maybe I want to set a blue and the other one maybe a red one, whichever you want. But basically this is kind of idea. And finally you just turn on the emission with a bloom and you get the kind of result. And if you want to instance points on the tip, then you basically just do a instance on points and take a UV sphere. Maybe we elongate this UV sphere on one axis, make it a little bit longer, and we basically join geometry. And then we need to alignment on the spline. And let's decrease the scale of it with a value precision. I am only going to instance at the endpoint. So what you can do is maybe endpoint selection. And then maybe increase its size. Right now they are using the same color. This is because for variances you need to realize the instance, or you have to change the shader, but anyway. But basically this is fine. Since they are using the same attributes for their random color, then you can see this tip and the trace are sharing the colors in this case. So at the end it's just kind of parameter things that you can just tweak this Falloff and so on. You can even duplicate this plane to elsewhere, so that because the Falloff is different, then they are going to have different values and behaviors and so on. But basically this is it. This isn't really a difficult setup, but I think it's a very interesting reference when you are working with it. So I hope you enjoyed this video. I'll probably see you next time. Bye bye.